Okay, so the other video dealt with basically goodness of fit tests, and now we're going to deal with association tests. So just because this is a silly example, but hopefully will help us make sense out of things, what I have here is we've got milk chocolate, dark chocolate, and then people who are less than 20 years old and people who are more than 20 years old. The question was basically just like, what's your preference? And I definitely cooked these numbers so that it would help us kind of understand what's happening here. So let's go in. So the kind of question we're asking here is, does age have an impact on whether people prefer dark or milk chocolate? And if I was going into this, I would definitely probably start with a null hypothesis that age does not impact the preference. And then the alternative hypothesis would be that age does impact preferences on chocolate. I've heard this theory before, and so now we're just gonna look at some data. And so this is theoretically the actual data that we ended up with. The question that we're gonna have to deal with though is, if this is the observed data over here, what is the expected data? And this isn't quite as straightforward as the last video that I made about a die, because you'd expect a die to be, all of the sides are even, but in this case, it's not like there's necessarily going to be like an even amount of people who like milk chocolate and dark chocolate. So in this case, what we're actually going to use is we're going to use the totals. If there's 150 people here who are less than 20 years old, and we have this particular split, what we really want to do is basically get equal percentages into the box. And here's what I kind of mean by that. If we've got 150 and 50 here, this right here is 75% of the 200, and this is 25%. And that means that in these two boxes, I should have 75, I should like evenly split this one, or not evenly, sorry. 75% is going to be up here, 25% is going to be down here. But then also what we need to consider is that on the bottom here, we also have a percentage split where we have about 40% here and 60% here. And that is what is going to control what the expected values are. Now, the formula that you would end up using for, say, this box is you would say 50 times 80 divided by 200. That's going to get you the value that you need. And if you work that out, you would find that that is 20. So I know that 20 is going to go in that box, but this is just kind of the formula. I want to go a little bit into the intuition of it. And so here I notice that we've got 75% up here, 25% up here. That means I should take this 80 and divide it into 25% and 75%. Well, a fourth, 25% of 80 really is 20, and three-fourths of 80 is 60. And you'll notice these numbers don't match, but that's okay because remember they have some static. This is our observed. This is what we would expect. And so what we're doing is we're basically getting proportional values here. And it will also work this way. It just happened that I used 80 this way, but yeah. Okay, so like for example, this 50 needs to be split into 40% of 50 and 60% of 50. Well, 10% of 50 is 10. JK, 5. I know what I'm doing. Don't worry about that. So 40% would be a 20. And then the other 60% over here would get you your 30. And then obviously, same deal every which way that you're going. If you want to just calculate this number, you can totally take and say 150 times 120 divided by 200. That will get you the correct number. Or you can kind of reason your way through this and say like, well, if 25% of 120 is 30, I need the other 3/4 of that here. That's going to get me 90 here. And that should work out definitely. 90 is 60% of 150, 60 is 40% of 150. Hopefully that helps. If you hate it, then just use this formula. It's totally fine. It's this number times this number divided by this number to get the corresponding box. Okay, so now we have observed, we have expected. We can just dive right in to the same thing that we did last time. And really what we need remember this is our formula for chi-squared, is that we're going to take the expected minus the observed. So how far apart are those? We're going to square them so we get a reasonable thing and divide by the expected. That will get us our chi-squared value. So I'm going to just start transferring over some of these values. So less than 20 and likes milk is 90. Less than 20 or more than 20 and likes milk is 30. And so filled in all of these for us. And weirdly enough, it ended up being 15 everywhere. But don't forget about this dividing by the expected value. So I've taken and divided by the expected values for each of those. And my sum is 25. So this right here is my chi-squared value. Now, because I have a 2x2 table, I also need to know the number of degrees of freedom. And if you look at that other video, you should hopefully be able to work out that there's only 1 degree of freedom, which means that we are looking at this curve where we've got 1 degree of freedom, and we are looking over here at 25. And I hope that you can just guess and see that that is a ridiculously small number. And in fact, if you work it out on your calculator, you will see that my p-value is hysterically small. That e to the negative 7 means that it is literally 0.1234567 likelihood. So this is pretty unlikely. It is just not true that in a world where age does not impact preference on chocolate, that we would get these numbers. It's just super duper unlikely. So this is going to let us reject the null hypothesis, get out of here, and we are then able to accept the alternative hypothesis that age does impact preferences on chocolate. Hopefully this helped. Let me know what help you need. Calculator instructions are in the Google Classroom. Hope you're good.